Hi, so welcome to the second video in Introduction to Trigonometry, and what we're going to do is look at a classic problem in engineering that sort of illustrates how we can use trigonometry to find solutions and find things like acceleration and movement, so a sort of dynamic approach. So we're going to look at a problem like this. So this is a classic inclined plane problem, and what we're doing is this could be any sort of object. It could be a car, it could be a vehicle. I believe one of the little activities that I've got for you is my chocolate Labrador, who does like sledging when it's nice and snowy. So we had a fun, and this is the thing about engineering, is you can ask questions that perhaps you wouldn't normally ask or you couldn't find the answer to. I was curious about how fast my chocolate Labrador, if I let him on a sledge, he does get on, but I wouldn't let him slide down a slope and might injure himself. But I was curious to know what the weight and the speed and the slope would do. So I'm modelling this as a very simple system, so sort of what we might call an adapted free body diagram, where we simplify the drawing and we just look at the forces that are involved. So I'm looking at this block, and my details are that I'm going to use a block of 50 kilograms. And we're going to look at whether this would slide down the slope. Now, some of the forces that are going to be involved is with regards to the friction. Now, I'm going to introduce the concept, but friction is quite complex, and so we won't get into too much detail about the nature of friction, but we will just look at the forces involved. Now, the first thing I want to do is label up my diagram, and I can draw this to some extent using a bit of scale. I can sort of roughly get, 5 centimeters would be perhaps 500 newtons. And in fact, we can simplify this by saying, well, if we look at gravity, we normally work at gravity at 9.8 meters per second, 9.8 meters per second. Now, some people do simplify it to 10. That's a perfectly valid way of doing a rough estimate, if you will. We won't do that today. We'll try and stick to the real numbers, sort of get into the habit of working with those sorts of figures. So we've got 50 kilograms accelerating at 9.8 meters per second under gravity. We'd have a downward force of about 490 newtons. And on my diagram, that would look like this. So there's 400, there's sort of 500. If I'm drawing a sort of scale drawing, it would be around here somewhere. So that's the mass due to gravity, and that's 490 newtons. So let's put that on there. I like to label up the diagram because it's useful you won't want to refer back to your forces, so it's a great way of sort of keeping track of everything. Now, what else is acting on this block? Well, the block is also sort of, if you will, this force is causing the block to act against this slope, and there's a perpendicular 90-degree force, what we refer to sometimes as the normal force. So I'm going to use a different coloured pen to illustrate that. And so we have a sort of force acting in this direction, and I've just mentioned the angle here. So we're dealing with 25 degrees angle of slope, and the nature of the maths is that this is also going to be 25 degrees. So we've got 25 degrees of slope here, and we've got 25 degrees acting against the mass due to gravity. It's starting to form, because there is also a force acting in this direction. I'm going to use a slightly different colour. The block sliding down the slope, and actually the magnitude of this force here is this calculation here. And we're starting to form a right angle triangle, as you can see, and therefore we can apply the orthogonals that we learned about earlier and deduce what the size or magnitude of these forces would be. This one's an adjacent, so if we go back to our classic SOHCAHTOA, and it's an adjacent, so they're going to use the cosine. So this would be the mass due to gravity multiplied by the cosine of the angle 25 degrees. Okay, so we're going to end up with 490 multiplied by the cosine of 25. So let's pull in the calculator and let's get that going. So mass due to gravity was 490 multiplied by cosine of 25 degrees. And the magnitude of that force then is 444, I'm going to go for 444 newtons. That's a great number. That's really, really interesting. So 444 newtons in that direction. Now, normally in engineering, if the block isn't sinking through the floor, it's not moving in any way, it's static in this scenario. So if there's 444 newtons in that direction, there must be 444 newtons in that direction, because it's in equilibrium. So there's about 444 in that direction. And this is sometimes referred to as a reaction force or a resultant. I'm going to just label it FR, 444 newtons. So I've labelled up the forces acting on my diagram vertically. Now I'm interested in this horizontal component, the amount of force that would cause the block to slide down, and whether that force is great enough to overcome the friction and actually allow it to move. So I'm going to calculate that force, which is, well, this is an opposite, and therefore I'm going to use the sign. So this force here, or the force here if you will, is the mass due to gravity, sine of the angle. And if we pull my calculator in like so, we can do that. So the mass due to, we've got mass due to gravity, 490 multiplied by, we're using the sine of 25 degrees. There we go. And that gives us a force of 207 newtons. I'll round that up. Do be careful when you're rounding. At 0.08, I would only round that to 0.1, so I'm going to let that go for the simplicity of working with the numbers. But the problem is, as soon as you start rounding, you create rounding errors. As you carry out further calculations, you can build on an error caused by an early rounding. So do be careful about when you decide to round. But for simplification purposes, I'm going to just round at this stage. Keep these numbers nice and simple. Now let me talk to you briefly about friction. So the friction, every single object obviously encounters friction. So you can hear objects on the table causing friction, but every object's friction with another object is different, and it's not something you can look up in a book. It's not calculatable. It has to be empirically arrived at. So you have to do some sort of experiment to work out specifically. And there's an actual example of this. There's an experiment that you can conduct using a tin of beans and a chopping board to establish what the frictional force is. What we do know is that when the frictional force overcomes the block, there's a point at which they're both equal. Now that won't be the case here. And once it actually starts sliding, we can look at the frictional force as being the ratio of the downward force being pulled and the resultant force from the block acting perpendicular or at 90 degrees to the slope. So if we look at that, it looks something a bit like this. I'm going to change because the green pen's not the most distinctive to see. So the frictional force, we'll label that FF, so for frictional force, and the frictional force is going to be equal to, now it's the coefficient of friction, and the resulting force, like so, would give me a downward force. Now for this particular activity I have looked up, because like I said it's a sort of icy slope, and the coefficient of friction between sort of something like a plastic object and an icy slope would be about 0.4. So I'm going to use that figure. So 0.4, and we know that our resulting force was 444 newtons. So if I multiply that, we've got 0.14 multiplied by 444 newtons. A lot of fours in that. And that's giving me a force of 62.16. I'm going to go for 62. So we've got 62 newtons acting or resisting movement in that direction. What I can do now is, and this is where I was saying about you can calculate and you can work out the sort of the acceleration of the block by applying another formula that you might be familiar with. So the force being equal to the mass times the acceleration, F equals ma. And if that being the case, then you can do acceleration being equal to the force divided by the mass. Now the force, well, we've got 207 newtons acting in this direction and 62 newtons holding it back in that direction. So the resulting force from there will be 207 minus the 62. So let's check that. 207 minus 62. So what is left is 145 newtons in that sort of downward direction. And if I divide that by the mass, 50 kilograms, divide by 50, and that's going to equal 2.9. So the acceleration is 2.9 meters per second per second. I hope that's useful. There is an example, like I said, in the attached document. There's a video that also supports that takes you through. It's called Percy's sledge. And once you've done a couple of these, you can start looking around at different objects. And actually, you can reverse this process. Like I said, there is an activity where you can use a slope. And I'll just grab an object here for example. If you have an object on a slope and you tip it at the point, and this is the key thing to this, is at the point at which it starts to move, just before that, the frictional force will have built up to be just about equal to the point where they're in equilibrium, so it's not moving. And at that point where it breaks away, you've got a good idea from this angle what the force is to overcome friction. And you can then use that to reverse this equation to give you the coefficient of friction for that object on that surface. Good luck, enjoy the experiments, and I'll see you in the next video.